Solution: carbon plus oxygen to give carbon 4 oxide. Delta H is equals to minus 393 kJ per mole. Hydrogen plus half oxygen to give water. Delta H is equals to minus 286 kJ per mole. Ethane plus 5/2 oxygen to give 2 carbon 4 oxide plus H2O. Delta H is equals to S kJ plus 226 plus 0, 2 times minus 393 plus minus 286. H reactant plus H product, but H heat of product minus heat of reactant is equals to delta H of reactions. H of reaction is equals to 2 times minus 393 plus minus 286 plus 226, which is giving us minus 1072 minus 226. Therefore, heat of reaction is equals to minus 1298 kJ per mole. Heat of neutralization. The heat of neutralization is the heat evolved in a reaction between a strong acid and a strong base per mole of water. Hydrogen ion plus hydroxyl ion to give water plus change in energy. Heat of reaction. Hydroxyl ion plus in bracket water plus hydrogen ion to give 2 mole of water plus delta H. Delta H is the heat evolved in the reaction. Acid, chlorine, alkali, sodium hydroxide. Heat evolved in kilojoule per mole is 57.3. Triisonitrates. Acid react with alkali, potassium hydroxide. Heat change in heat is 57.3 kJ per mole. Half of tetraoxosulfate 6 plus sodium hydroxide to give 66.5. Heat change in heat. Hydrogen tetraoxonitrate plus potassium hydroxide to give 58.4 change in heat. The heat of neutralization of a strong acid with a strong base is approximately constant and is about minus 57.3 kJ per mole. This is because the reaction of a strong base involves mainly of the reaction of the hydroxyl ion and hydrogen ion or hydroxide ion. In neutralization reaction, ionization of the base must first take place to produce hydroxyl ion. The heat change observed is thus the heat of neutralization of ionized hydrogen ion. Example 4. In an experiment to determine the heat of neutralization of 0.1 molarity of hydrochloric acid and 0.1 molarity of sodium hydroxide, the following results were obtained. Mass of 50 cm³ of hydrogen chloride is equal to 50 gram. Mass of 50 cm³ of sodium hydroxide is 50 gram. Initial temperature acid T is equal to 32 degrees centigrade. Final temperature of the mixture T is equal to 46 degrees centigrade. The heat capacity of the solution formed is 4.2 joule per gram per coulombs. Calculate the heat of neutralization between acid and base. Solution. Initial temperature of acid is equal to 32 degrees centigrade plus 273 to give 305 Kelvin. Initial temperature of base is equal to 32.7 plus 273 to give 305.7 kilo Kelvin. Initial temperature of the mixture is equals to that 305 plus 305.7 divided by 2 to give us 305.4. Final temperature of the solution is equal to 46 plus 273 to give 319 Kelvin. Rise in temperature is equal to 319 minus 305.4 to give 13.6 Kelvin. Mass of mixture solution is equal to 50 plus 50 to give 100 gram. Specific heat capacity of solution is equal to 4.2 joule per gram per degree centigrade. Heat evolved is equal to mass times SP, specific heat capacity, times time, which is equal to 100 times 4.2 times 13.6 Kelvin to give 5,721 joule. Since the reaction is exothermic, heat evolved is minus 5,712 joules. Equation of reaction. Hydrogen chloride aqueous plus sodium hydroxide aqueous to give sodium chloride aqueous plus H2O liquid. The heat evolved is based on 1 mole of hydrogen chloride reacting with 1 mole of sodium hydroxide. Therefore, heat evolved H is equal to 5,712 over 0.1 to give 57,120 joule or 57.12 kilojoules. Chemical equilibrium. Consider a simple reversible reaction given by the equation A plus B equals to C plus D. The rate of forward and backward reaction depends on the concentration of the reactant. Figure 17.3. The rate of forward reaction will be highest at the beginning because the concentration of A and B are also greatest at this point. Equilibrium of reaction. For concentration graph, plotting a rate of reaction against time, AB to give CD and the CD to give AB. As the reaction proceeds, the concentration of A and B of the reactant decreases. Sooner or later, the rate of forward reaction will equal the rate of backward reaction, and a dynamic equilibrium is set up. A state is established in which the concentration of A, B, C, and D no longer change. This is known as the state of chemical equilibrium. Factors that affect the chemical equilibrium and yield. This may be predicted by Lechetelle's principle of the law of mobile equilibrium. Lechetelle's principle. The law states that when a system in equilibrium is disturbed, the equilibrium adjusts itself in such a way as to cancel out or annul the effect of the change. The main factors affecting the position of equilibrium are concentration, pressure, and temperature.